right, good. So Steven works at Comp3 as a machine learning engineer and a researcher. He's been doing a number of different technologies, variational autoencoders being one of them, but he's worked with image recognition work, probabilistic models, and a number of other things which you can obviously talk to him about. He has a PhD from the University of Michigan, and he's going to talk to you today about specifically variational autoencoders for image generation. All right, thanks, Stephen.
Great, thanks, Jason. As Jason told you, yeah, my name is Stephen Flores. It's great to meet you. I also want to thank Dave and Redis Labs for hosting us here in this wonderful venue. And as Jason mentioned, I'm going to talk about something called variational autoencoders, and specifically we're going to look at it for the task of image generation. Now, just a little bit of background about what Jason and I are thinking about doing here. And I don't want to overcommit us to anything, but we were kicking around different ideas for fun things that we can do in the cognitive computing enthusiast group here. Here we all are. And you know, we've seen some stunning results coming out of generative models lately over the last 5 years. I'll show just a few examples of that. And we thought it would be a lot of fun to, you know, take a look at some of these models and play around with them, and then present some of the things that we create to people here, and kind of give this a little bit of a feel of simultaneously a talk, but also kind of a study group. And then maybe provide some resources that we've created to you guys that you can take a look at and play around with and give us feedback about. Tell us what you discover, what we could improve, and kind of keep this a conversation. And then maybe in the future we'll do yet another part, taking another model in this area and do something cool with that. But today we're going to start with variational autoencoders. Before I go into what those are, let's just sort of open up the topic. Do you recognize anybody here? Do you know anybody? Anyone look familiar? Yeah, kind of. Kind of? Well, you know, unless I misread the paper, you shouldn't, because none of these people are real. All of these images were in fact generated by a random seed that was fed into an algorithm. So that algorithm is something that I'm not going to talk about today, but is in the same area of generative models for, you know, image generation. It is called a generative adversarial network. And these days, we've got these models producing very high resolution images. I think these are 1024 by 1024 by 3 of fakes of faces. And it's very hard, at least for me, to, you know, try to look and find the defects. These are so compelling. And, you know, well, celebrities being celebrities, it's a very hard job, but it is kind of their business to look as good as possible. So trying to spot the defects on faces, it feels, I don't know, a little bit unkind. But let's just try. So I was like looking around a little bit earlier today. Let me see if I can do that here. I think if we look at the bottom part here, there's something a little bit funny happening with her tooth in the corner. And, well, this person doesn't exist, so I don't feel so guilty in pointing out blemishes. This is the computer's fault. I think this person up here, the best I was able to find that could maybe be an issue is that, you know, her lip over here, some of the pink kind of ends before it should. But, I mean, you have to look really that close to see, you know, where the defects might be in this particular example. And this is like one of the state-of-the-art models. So most results that you see from generative adversarial networks don't look quite this good, but they're still pretty impressive. So let me go ahead and talk about some applications of generative models for images before I go into what variational autoencoders are specifically here. So one clear application is image editing. So you've got a bunch of images or some video, and somehow it isn't doing what you want. So in this toy example from this paper, we want our zebras to be horses or vice versa. And in fact, you can do this here. And you can take a look at the papers that are shown at the bottom here to see how they do this exactly. Another one from the same paper is the idea of style transfer. So a typical example of this is you have a scene that displays a particular season, and you want to change that season here. So this is in fact something that you can do, and in fact these results are getting more and more convincing. So another application is pose interpolation. So one issue with face recognition systems is that if the face is turned too much to the side, it's hard to even detect that you have a face anymore because you're not going to see two eyes and a mouth. It would be nice if we could take a side view of a face and somehow gradually turn it into our best sort of guess of what that person might actually look like if you were looking at them head on. Whether or not the result would be reliable enough for some sort of facial recognition system for some kind of job like identifying somebody, I think is still a pretty open question. But the fact that you can actually do this and produce a reasonable guess at what that person looks like head on, I think is pretty impressive. Yet another application is image repair. So we have some kind of defect in our image here that's modeled by just putting these white squares here. And the question then is, can we fill in the region of the white square somehow to create what looks like a compelling original image? Obviously the interior will be fake, but are we doing a good job at that? There are kind of mixed results here. They're pretty impressive. Let me just say that they're really impressive compared to what I understand the options would be before deep learning and these generative adversarial networks took hold maybe within the last 5 years. So I mean, previous to this, there wasn't really a ton you can do. It was kind of a boundary value problem, a discrete boundary value problem where you know what's happening on the boundary and you create some kind of model, some kind of Laplacian model, some kind of minimization criteria that would tell you how to propagate pixel values into the interior, and then colors just kind of bleed in. And if you have something that has detail to it, like looking at this boat example here, we want to continue these black lines inward into the white square. Models like that I think would have done a pretty poor job, but this model over here is actually doing a very impressive job. I especially like this boat example because the white box over here is hiding the boundary of this boat completely, and yet somehow this model still knows to continue the boat to some endpoint and then fill in the rest with scenery. So I mean, to me this is absolutely stunning. Yet another application that that's out there is this idea of image synthesis. So somehow we have partial information about the image. In this case, we have segmentation of the image into its components. This looks like maybe the scene from a street. As you can see, things that look like cars and traffic lights. And the idea is, using only this boundary information, we want to fill in the pixel values in some compelling way to have something that looks like an image that we would see from our eyes or a camera. So cars should look like cars, road should look like road. And this is the result here. And again, it looks pretty impressive. I mean, there are some clear defects that I can see. The road maybe doesn't look quite as level as it should. There's a little bit of blur over here. But, street signs more or less look like street signs as they would in Europe. Details like that are difficult to get. And so, yeah, these are pretty impressive results. And so, I mean, I think that it's clear that there are many, many different problems out there that one can, try to solve with these kinds of, this broad class of models. The applications, I think, from an industry perspective are kind of clear. Broadly speaking, you have some large amount of image or video data, and it contains some kind of imperfection, or it's not doing something that you want. For example, you wanted zebras, but you had horses, right? Maybe horses are just a lot cheaper. So if it was somehow easy or reasonable to kind of perturb your data off of a horse's manifold or whatever it's living on just a little bit into some kind of zebra manifold instead of actually having to go out and get zebras, well, that's ideal. So you can see things like that. That's sort of one very specific case study. You could dream up a million case studies that are like that industry could find use for here. So these are a really big deal. So that was sort of the the warm-up and temptation to tell you why we should care about this area of machine learning right now as it becomes very hot. So these are the contents of our talk today. I'm going to start off by just giving you guys a couple slides, or like 4 slides of a survey of different generative models, and ending with the one we'll talk about today. And then we'll launch into those models, variational autoencoders. That will be part 2. And part 3, we're probably just not going to have time for, but I actually have a PhD in math, so I couldn't resist the temptation of writing down a lot of integrals. But, you know, we're not going to have time for it, and we're going to take it kind of easy. So I'll leave those slides in there for you guys to check out later on if you'd like, in case math is somewhat frightening, or at least the calculation side of it. Don't worry, I'm not throwing calculations at us. We're not doing that. We've already worked all day, probably. So, but yeah, just take a look, because it provides yet another perspective on these things that I'm not going to go into today, but is really, I think, well, it is the original way these objects were conceived. So, yeah, let's begin with just a quick survey of 3 classes of generative models for images that I've encountered. One is called pixel RNN here. And unfortunately, this slide is very dense. Perhaps you shouldn't read all that much about it, in as much as just look at the image here, and let's just go with that. So the idea is we want to generate an image pixel by pixel. And the way this model approaches that task is as follows. So if we're working on, let's say, the red pixel value here, and all of the blue pixel values have already been determined, then the red pixel value is going to be determined or depend on only the blue pixel values that came before it. So the generation of the image is starting at the upper left corner, proceeding rightward and downward. And the dependence is captured in the form of a recurrent neural network, where the red square depends directly on the blue squares to the left and above it, and then those squares in turn depend on their squares to the left and above it as well. And so there's a hidden layer that feeds that information in to determine what pixel value the red square should be. And if you go through everything in the paper that introduces these, they have an explicit intractable maximum likelihood function that you need to optimize in order to create a model that creates compelling images. And it's pretty good. As I mentioned before, there's another class of models that are just completely on fire right now, generative adversarial networks. They're producing, it seems to me, the best results out there right now, and have been doing so for maybe the last 2 or 3 years. And on top of that, they come from a really cool idea. And the idea is as follows. This network here, well, this model comprises 2 different sort of submodels, or networks here. So the first guy over here is called the generator. And this is simply a neural network, all right? So that's a mathematical function. It's linear functions composed with activation functions that are not linear, but otherwise very simple. You feed random noise into the input nodes, and the output is something. And you hope that the output looks like an image. So, for example, maybe an image of a bird. So I've found a hand-drawn picture of a bird to take the place of a fake image here. And we may also have a real image of a bird as well, living on the side. In order to tune this network here, to tune the weights over here that specify how I'm going to go from input to output, to create really good output fake images, I'm going to take real images and fake images and then feed them into another network called the discriminator. And the discriminator's job is to determine, to classify each image as either real or fake. And so you have these 2 different components that are competing against each other and trying to win. So the generator wants to do a very good job at creating fakes. The discriminator wants to do a very good job at distinguishing reals from fakes. And as they compete against each other, the idea is that you have 2 very good competitors. And then you can, well, eventually throw away the discriminator, and then you have a great generator. Yes?
I don't quite understand how the generator learns.
So
it puts out junk, how does it learn?
right, exactly. And that sort of leads to my next point. Now, I mean, I can't speak about this coming from the point of view of an expert because I actually haven't dove into these models yet, but I really want to because they're doing some really cool stuff. But these models are actually really tricky to train because of exactly that situation. If you want to personify these as two different people competing against each other, if you know, if it's poker and this guy's just like a world-class player and this person's new to the game, it's going to be extremely difficult to learn. You're just going to get hammered every time. So there are different tricks that you can use to kind of avoid these situations and converge on the right equilibrium of two really good players against each other. One of the more elementary ones that people have used is just allowing maybe the generator to update more often its weights than the discriminator. So that way it has more of a chance to learn. Perhaps that works if you think of the discriminator as having maybe a slightly better job to do. I mean, at least intuitively, I would think it's kind of harder to figure out how to draw a good picture of a bird than it is to figure out if it's real or fake. So, but there are a lot of other techniques out there to make these things do their job. And there's a whole zoo of these models. This is just sort of the most vanilla version that you could have. So I really encourage you guys to check out everything going on there. There's just a ton to read and learn about. So the third model, and the model that will be the focus of what we talk about today, is called a variational autoencoder. And these models are really cool, as you'll see pretty soon. Unfortunately, they seem to be lagging behind, at least currently in the business of image generation, but they have tons of other applications out there. And they're, you know, for that reason, they're, you know, still, they're not obsolete. They're totally worthy of study and very interesting. They also have tons of generalizations, and there's a whole zoo of these guys that do very good jobs at different tasks. We're going to look at them today, though, in the context of image generation, because, well, when you have slides, image generation is, you know, a very easy thing to show. And the results are really nice. A lot of the things that I'm going to show you aren't, you know, current, hot off the press. These are kind of results that have been kicking around for like the last 4 or 5 years, which in Silicon Valley terms is kind of ancient history, but at least accessible to, you know, people with a laptop this humble. And, well, as we'll see, you can use Google's Collaboratory for GPU support, and you can do a lot of fun stuff locally at home. So I won't explain the architecture. We'll see it again, and there it'll make a little more sense to talk about what you're seeing there on that slide. So that's sort of my very bird's eye view of a bird's eye view of what's going on right now in generative models. Moving on now, let's go ahead and talk about variational autoencoders. So there are a couple different ways that you can approach variational autoencoders. I think probably the most intuitive way to approach this, and this is what I found for a lot of people writing about it, is to first look at a related model called the autoencoder, which is trained to do a very different job, actually. So the job of an autoencoder is to learn a low-dimensional representation of high-dimensional data. So a lot of times when you're working with some, you know, data set, it's living in some very large vector space. So it's got, you know, hundreds, thousands, maybe even millions of components. But if you actually looked at where your data lied within the realm of all numerical possibilities in that space, that region is actually really small and connected somehow and has some structure. And it would be very nice if we could kind of peel away all of that ambient space, which takes up a lot of memory, and compress our data points down into some smaller representation. And there are a variety of algorithms that do this job already out there. One of them is called the autoencoder, and I think that this became more popular when neural networks really started taking off here. An autoencoder has two components to it, like a generative adversarial network does. The first component is the encoder, so that's going to map our data point down to some vector that has far fewer components to it. and that vector is living in something called this latent space. And the result then can be passed through a decoder function, which tries to act like an inverse function to reproduce the original data point. And you're going to do a good job at this task if the original data point that you fed in is close in some distance metric that you provide to its reconstruction on the other side. So that's sort of the goal of these things. So this is the macro architecture here of an autoencoder. Microarchitecture, so exactly what are the encoder and decoders made of? These days, they're made up of neural networks with some kind of topology to them. I'm showing a fully connected here. And so how do we make an autoencoder really good at its job? Well, just skipping back here for a moment, these connections over here, if you're familiar with neural networks, are all given by just addition and multiplication by weights and biases. These are just parameters that you would like to assume really nice values so that you do a very good job at your task at hand, which is taking in data, sending it to some low-dimensional representation, and then expanding it to the original thing. So in order to get those weights to achieve their desired values, we want to create something called a loss function. And this loss function, if it can be minimized by changing the values of those weights to appropriate numerical values, we will then be left with an autoencoder that then does a very good job at its task of compressing data and then decompressing it to nearly the correct form. So what is a loss function that will characterize the task that I've just described? So a loss function that would be appropriate would be to basically just take a whole bunch of data points in some training set that you have, pump them through this autoencoder, encoder-decoder pair, and then take the output data point, the reconstruction, and then force the input and the outputs to be very close to each other with respect to some distance function here. And there are different distance functions you can use out there. A common one that people use is, L2 difference or Euclidean distance between points in a vector space. So if you can make this loss function very, very, very small, then your autoencoder is doing a very, very good job. And you're doing that by changing those weights in the network, which I'm not showing explicitly here in this equation. And you can do that using gradient descent. So, okay, well, this slide is basically, saying what I just said earlier, except there is one slight change. And that is that when you ultimately go and evaluate the quality of your autoencoder, you want to turn its attention to some kind of separate validation set. So data that is totally apart from the training data. You want to do this as a kind of sanity check to see that you haven't created a model that is only good at encoding exactly the data that you showed at it. That is relatively useless, unless that is truly the only data you'll ever work with, which in most applications is not the case. So that's sort of a bird's eye view of what an autoencoder does and what it looks like. And I'd like to show you some examples of this, turning our attention to two very well-known image data sets and taking this for a test drive. So the first data set, I think a lot of people will be familiar with. It's called MNIST, a very famous data set of about 70,000 images of handwritten digits. And these are great to work with because this is image data that is relatively low dimensional and easy to work with. You can train models on it using just a CPU and a humble MacBook like what I have right here, and it doesn't take very long. So a great way to do experimentation and sanity checks before moving on to more complicated data sets. And this is the architecture of my encoder and decoder here. So just the different dimensions of the layers as I'm pushing data through it. All layers are fully connected. And then this is what the results look like for a validation set that is not seen during the training process. So 5 goes in, 5 comes out. I'll explain what you're looking at in the middle in a second, but first we can acknowledge that except for some of the blur, what has come out reasonably looks like a 5. If you had to pin it to any particular number, either a 5 would win or an 8 would win, but I think an 8 would be a distant second in this case here. So the stuff in the middle here, these are the encodings of all of the points in the validation set that I used here. And they're colored by their numerical value. And one thing to notice here about this set is that it is not isotropic. So it's distributed out in different directions. And as a result, if I take, as I've done here, a red circle and throw it down on these points, a red circle that contains essentially all of the points, only 99% in this case here, you can see that there's actually a lot of white space that is not touched by any of these points here. And that's not a problem for our current application, but we'll see that we'll have some issues with that when we move to the application of image generation. So now let's move on to another data set that is a little more complex and interesting to use, Celeb A. So this is a data set of over 200,000 images of celebrity faces. So as you can see from the architecture here beforehand, I've cropped the faces out to 64 by 64 by 3 images. And I send them through an encoder, which is now a convolutional neural network, down to the last layer, which is fully connected. And then in that latent space, I have 100 dimensions. And then I do the opposite, moving through these deconvolution layers, expanding back up to, well, what we hope is the original image over here, but at least a tensor that has the same dimensions. So let's look at some of the results that we got from this. So similar to the digits, we see that the input, which is given by the first, third, and fifth, etc. columns, are similar to the outputs given by the even columns, but the outputs have a little bit of blur to them, which is not ideal. So we're learning something, and in some cases the results are actually pretty good, but in other cases the blur is more than we would like. I'm looking at these guys in particular, and this could be for a variety of reasons. I didn't train with all that many images. I think I only trained with 15,000 in this case. The latent space might be too low dimensional. That could be another issue to experiment with. So, as is the case with, developing ML models, searching, the hyperparameter space of architectures and learning rates and things like that is sometimes a very tricky matter, though, there are new technologies that can help with that. And, some of the problems that you may be seeing might be symptomatic of the model that you're using. It can only just do this well, and then other problems might have to do with the fact that you're just not really living in the right, part of the hyperparameter space. But, we're getting faces out, and the faces look like the faces that went in, so this is reasonable. Now, autoencoders were trained for the specific task of data compression, but now we're going to turn to a tempting application of data generation. That is to say that after we have trained our model, let's consider the idea of throwing the encoder away completely and instead feeding a random sample from the latent variable space into the decoder and wondering what would we get out. And we would have in mind what kinds of things we would want to get out. If we're working with image data, then we'd like to see something that looks like an image, or even better, an image of something recognizable, like a dog I have here. But sadly, more often, we might just get noise coming out here for any random sample that we feed in. So this is kind of a tricky thing that I'll show you in the coming slides with just a simple autoencoder. If you try to do this, then a lot of times you're going to end up a little more over here than over here. Well, at least for MNIST. If you're working with very complicated data sets, like pictures of animals, then you're very rarely going to hit on something like that. Lots of luck. So let's just sort of look at what happens with our model when we do this trick with digits. So a point that I didn't mention earlier is that with the MNES data set here, we're compressing down to a two-dimensional vector space, which I want to point out is a really strong compression, because the original images are 28 by 28. So we're cutting off all but 2 dimensions. And you know, it's pretty surprising that we can get digits out of the decoder with such a strong compression. At least I'm really surprised by that. So just keep that in mind when you're looking at these pictures, that these are genuinely two-dimensional variables or vectors living inside of a two-dimensional latent space here. And you know, you'll recognize this image from several slides back. These were the images of all of the handwritten digits in our validation set. These are all of their encodings now. And this is the red circle that surrounds almost all of them. And as I mentioned before, these encodings, when taken all together, form a set that is not isotropic, and it leaves a lot of white open space inside of the circle. And so if you were to just sample this circle in a very naive way, by, for example, throwing down a lattice and taking every single lattice site and just passing it through the decoder, what would you get? And actually the results weren't too bad, but they're not perfect. So just for the sake of me making the points I want to make, let's dwell on some of the imperfections, and then I'll amplify it a little bit on the next slide, and you can maybe buy what I'm saying a little more. So yes, there's a lot of open white space that these lattice sites are sitting on top of that are not near any of the actual handwritten digits. So where are some of those examples? Well, off in this corner we had some of that space, and we can see that these lattice points are mapping to things that they kind of look like ones, but honestly they're pretty diagonal. So it's not great in terms of just sending in some random lattice point and reliably getting a number out that you would want to pass off. But it gets even worse when we move to a more realistic compression space. So recall that we're compressing down to 2 dimensions. And there's a lot of loss when you do that. And part of the blur that you see in the image outputs can be attributed to that, though it is also arising from other things. So what happens if we move to a higher dimensional latent space, like, for example, 10 dimensions? You can imagine all of the encoded points in from the handwritten digits in our validation set. You have a lot more space now to move out in 10 dimensions. So you're going to have some shape that is now highly isotropic, that can have all kinds of fjords that are diving down into it. And if you want to create digits out of the decoder, well, you want your random sample to lie close to this very strange cluster. That's going to be a very hard thing to do if it has some crazy shape, as it can, you know, assume in a much higher dimensional space. So what have I done over here? I've taken the 10-dimensional hypersphere that's going to surround 99% of the points in that 10-dimensional space. So this is for, by the way, a different autoencoder model where I use 10 dimensions instead of 2 for the latent space. So I'm going to take that 10-dimensional hypersphere and I'm going to cut it, you know, across in, using the first 2 components of the 10-dimensional vectors and create a great circle out of that. And this is what that great circle would look like from a bird's eye view. Lay down lattice points, say these will be my random samples, and then push them through. And what I get is worse, because I have this big empty hole over here where I just hardly get anything out. So this must correspond in that 10-dimensional space of some fjord cutting into my collection or my giant cluster of encoding points. So that's difficult because this is a more realistic, you know, dimension for a latent space to try to compress down to. So this is problematic, and one that we'll try to look at fixing using variational autoencoders. Now, we can also turn our autoencoder to the task of face generation. And these are some of the results that we get here when I feed in normal random samples into my decoder that I created in that previous model. And the results look like faces, they just don't really look like pretty faces. We would want to do better in some pretty evident ways. And we will do better by introducing variational autoencoders soon here. So this is just sort of a summary of some of the limitations that I talked about before. And it may be clear that a good resolution to this problem would be to somehow tweak our model a little bit in some way that could maybe cause our encodings to fill out this circle that surrounds them and give them a more isotropic shape. So that way it's easier to sample randomly the vectors in this latent space and then get good results out of the decoder. So then this leads to variational autoencoders. So what are variational autoencoders then? They're autoencoders, but they have some probabilistic elements that are mixed into them. Their origins come from Bayesian inference, which we're not really going to touch on over here. Instead, we're going to talk about it in a more direct way about how it's different. So instead of mapping points to low-dimensional points, data points to low-dimensional data points in a latent space, a variational autoencoder, its encoder will take those data points we have and map them instead to probability distributions. And specifically, those distributions will be Gaussian, multivariate Gaussian distributions. So in order to map to one of those guys, you really just need to specify the parameters for that distribution, its means and variances here. So that's going to be the output of the encoder part of the variational autoencoder. And then using those, we do a random sample to generate the latent variable that will be the compressed image of the original data point. And then we take that result and then we feed it through a decoder. So that is the first difference. So the encodings are now kind of fuzzy objects that are fixed to a particular value through a random draw. In addition to that, we're going to add an extra term onto the loss function called KL divergence. So KL is an acronym that stands for the two people who worked on this aspect of information theory. And if you want to know more about all of that, you can turn to Wikipedia and many other great resources. So what is this term responsible for? So recall that we're mapping our data points to distributions now. So we would also like to impose the constraint that those target distributions lie as close to a unit normal distribution as possible. So zero mean and standard deviations all 1. And why would we want something like this? Well, this could have the effect of causing our points to spread out within that red circle I was showing earlier and form a more isotropic distribution of means generally close to 0, standard deviations generally close to 1, radiating outward from that center point of 0. And when we have a structure that's like this, that makes life a lot easier when it comes to making random samples to feed into our decoder and generate random images, because all we have to do is draw from a unit Gaussian. So, this is a sort of very constrained system over here. We've specified a lot of what this should look like. We've said that all of these mystery distributions have to be Gaussian, and they have to be very close to a very nice Gaussian. So, given these constraints, is all of this going to produce a reasonable model? And it does, actually. So the first thing we're going to look at is the task of reconstruction. So this is somehow something that we don't want to lose our ability for when from autoencoders. We want to be able to do as well as we previously did there. And I'd say that we're basically on par over here. Once again, a 5 goes in and a 5 comes out. And yet we're still pulling this off while having, on our validation set, a more isotropic distribution of our encodings. So that is a nice thing to see. It looks like we haven't paid too much of a price, at least for this sample, to impose these constraints here. So for the task of digit reconstruction, let's give it a pass. And let's now turn to the task of digit generation. So once again, we're going to do the same thing. We'll just randomly sample all of these lattice points, feed them into the decoder, and this is what we get out. And I'd say that it's marginally better than what we had before. I think more of these things look like digits. I need to be a little bit careful. My brain obviously wants me to think that. But I think that the next example that I show you will be a bit more compelling even. But it is pretty cool to even see this. These are the results that you get when you do the same thing using a 10-dimensional latent space for a variational autoencoder instead of a 2-dimensional space. And we see things that look almost everywhere like digits, which if you do the side-by-side comparison of the autoencoder to the variational autoencoder using a 10-dimensional latent space for both, you can see that the random sampling fed into the decoder did a better job for the variational version than it did for the plain autoencoder version here. So this shows us then that variational autoencoders do seem to do a better job at digit generation when fed random samples from this hypersphere that's surrounding all of our validation encodings. So there must not really be any deep fjords going into this, cluster of encoding points in our latent space. Now, I think it gets even a little bit more compelling when we look to faces, because we're wired from infancy to want to look at faces, I'm told. So let us do that. On the task of face reconstruction, we're doing about the same, it looks like, as an autoencoder. And a few slides, I'll show things more side by side so you can really compare these different versions. But this is, similar to the slide that I showed before. It's just that in the even columns, I'm now showing the output results of the variational autoencoder. Again, this is only done with like 15,000 faces. So you can do better if you use even more faces. But yes, you still do have this residual blur, which is something that has kind of plagued variational autoencoders always. And one of the goals is kind of to get rid of that using different tricks and methods. But the task of face generation is quite a bit better. Again, there is a lot of blur. And yes, we could do better if we used yet even more data and trained it for longer. But we have at least more or less solved one problem, and that is that we had these giant blotches within these generated faces that were output from just the plain autoencoder. And more or less, those kinds of things seem to have gone away. So, and this is all just done by just, doing normal, random normal draws of a latent variable and feeding them through this decoder network that we trained. So then this is the side-by-side comparison that shows the face reconstruction quality. Autoencoder is in the, okay, well let's just start off. Originals are obvious because they're sharper images. Autoencoders are the middle column, and then the variational autoencoders are the right column here. And this is how they compare for face generation. And I think that the variational autoencoders are doing quite a bit better. They suffer from more blur, and as I've mentioned a few times already, you can turn to the literature for various tricks, or I think in this case, because I was using so little data, I've just used even more data to get better results than this. But a lot of this weird stuff, like these giant patches or the slanted eye that's kind of creeping off to the side, these effects seem to have gone away for the most part here on this side. So pretty cool. So this works. Here's another cool thing that you can do that I really like. So with variational autoencoders, the encodings are living in a subspace, this latent space, that is easy to sort of live inside of. And what I mean by that kind of goes something like this, right? So what if we wanted to, as I motivated at the very beginning of this talk, what if I had an image of a face and it was just, I don't know, very expensive, or the model for the picture was just not available, and I wanted to change an attribute such as hair color for this face? Could I do that using these models? And in fact, I can do that using a somewhat naive approach that works surprisingly well. And the way we can approach that is as follows. So if our faces go in with labels, as they do with this data set, then we can take all of the faces that are tagged with blonde hair, compute their encodings, find the center of mass of that, and there'll be some point living inside our 100-dimensional latent space. And you can take all of the faces that do not have blonde hair, they're tagged as such, find the center of mass of all of those points in the latent space, take those 2 points, 2 vectors, and take their difference. And that difference is ostensibly the direction that you should walk in if you're starting with an image of a face that is not blonde and you want to get to one that is blonde. Now, there's no reason necessarily to think that something so naive should work. Who's to say that a linear path from, one face to another along this direction is going to take you to this endpoint over here? And yet it does. The neat thing is that you can do this sort of face interpolation where in the decoder output space, which remember is this very high dimensional space, it's very easy to leave the image of a face and move into just noise. You still somehow stick on side of that manifold and the hair color just gradually changes. And you can do the same thing for other features, such as in this case I've done shades here. And you can also do both at the same time. So there you have it. So here you can see in action some of the applications that we talked about in the opening slides. And all of this is not terribly difficult to do if you have access to a GPU, as you can get, and I'll talk about that in my last slide here. And you can do all of this on your laptop. So really neat stuff. So this is just a summary of some of the pros and cons of variational autoencoders. So pros, these models are really good at not just data encoding and reconstruction, but also good at random image generation. It's really easy to sample their latent spaces and get compelling images out. And what I've shown you is just the most vanilla version of a variational autoencoder that there is out there. There's a whole zoo of these things that do much better job than even what I've shown here that you can look at. And they're reasonably easy to train, unlike generative adversarial networks, which I talked about earlier on being kind of unstable and difficult to train. Though some of those issues have kind of gone away with a lot of tricks that have come out over the years. And that's why these guys are kind of pushing ahead right now and showing us really cool stuff. Some cons are that a lot of times the images that come out are blurry, and there are different reasons for this that people have put out there and different workarounds that have generated better results. But I feel like a lot of times when you read about VAEs in the literature, that is like one of the key issues that they're somehow trying to reduce. And that doesn't seem to come up so often with GANs. And they're as I understand it, they're not quite pulling ahead today, at least in the application of image generation, but that may not be the worst thing in the world and make them obsolete. Okay, so without elaborating, I'll let you kind of read about a couple of the enhancements that I talked about at the beginning here. But while I'm on the topic of this idea that GANs are somehow outpacing these things, I actually think that a very natural combination of these guys is to put GANs in variational autoencoders together. And I don't know that I see a lot of people doing this, though there are research papers out there that have done this, and there are some GitHub repos out there that you can clone and experiment with that do this in TensorFlow. But you can see by looking at their architectures that the decoder from the variational autoencoder and the generator are basically doing the same job. So the generator is in the GAN. They're doing the same job of creating an image. So you can actually kind of overlap them, pair them together, and use a discriminator as sort of your loss function to try to determine whether or not the image you've created is realistic. And you can pair that off with other more traditional loss functions like pixel to pixel loss or other loss functions to train your network and get something that produces really nice results. So I don't know that I have a lot of time. I think I actually have no time.
5 minutes or so.
Oh, 5 minutes.
Because they can download this, right, or go and look at it, right?
Yeah, I haven't pushed it to the repo yet, but I can do that tonight.
Okay.
So what I'm showing you guys is something that I intend for you to have access to. Now, bear in mind that this is only internal research, internal meaning inside my mind, so I haven't like wrapped this in a bunch of unit tests, the warranty, there isn't one. I would bet my life that there are things about this that are somehow broken, so, you know, point out any bugs to me. At least got, what is that? That's very odd. My desktop is now extremely small, and I think that's because I'm plugged into...
It was the same thing with Dave's.
Yeah, it happened to me too.
Okay, is there... Well, here. While it's very small, I think I could just blow this up, right? Oh, gosh. If I just do the minus thing?
Yeah, plus.
Or plus, yeah. Okay, that'll do it. Okay, Jason saves the day.
Maybe one too many.
I don't know, you know. I'm starting to become a little bit more of a senior citizen, so bigger is better for me. Yeah, so, all right, well, this notebook takes about 10 minutes to run top to bottom. So maybe I won't do that for the demonstration. I'll just sort of do this streaming consciousness scroll through, and we'll try to all hold on, because I know that I kind of drop off after a while of like scrolling. But this is a notebook that you guys should be able to download once I push this to the repo tonight. And you can run it top to bottom to basically execute most of what we've seen for the Celeb A data set and reproduce all of those images earlier today. Let me tell you a little bit about what you're looking at here. So how many people have used these Jupyter notebooks for, you know, toying around and... Okay, so yeah, so a lot of people, it's a great environment to live in when you're messing with data, or you're just trying to prototype something before, you know, getting serious with it. See if it will work. So how many people have heard of Collaboratory? Okay, so also quite a few people, but not quite everyone. So I heard about Collaboratory about a year ago when I was out on the playground with my kids. There's one outside of our apartment. My wife is a graduate student at Stanford, and I was just griping about the fact that I don't have a GPU, I can't do any of this stuff. And he's like, just use Collaboratory. I'm like, what is that? So Google has this Jupyter Notebook environment that is allows you to use for free and with reasonable limitations a GPU. And I'm trying to remember where I find that guy again. I think it's under restart and run all, reset. Change runtime type, that's it. Yeah, exactly. Now, be careful. Actually, I think the first, I don't remember exactly what happened, but I think the first time I entered this environment, the GPU was there as a default, and I was like, okay, great. And then the training was still slow after a while, and I was like, oh gosh, what is going on here? Maybe my data sets actually takes longer to process than I thought. I didn't sit down and do any arithmetic to see if what I was looking at was reasonable. And it turned out that for a while I actually was just training with the CPU, and I wasn't smart enough to just double check and make sure that it actually was using a GPU. My understanding is that the default will be a CPU, and you actually have to go into that spot there and click on the GPU as opposed to none. They have this thing called a TPU, Tensor Processing Units. I don't know a lot about them. I think they're a heck of a lot faster even than a GPU, but they might be more specialized to the task of training ML models or specifically neural networks. I don't know a lot about them, but maybe you could also give that a shot too. I stick with the GPU here. And once you have that, what are you going to look at here? So if you're familiar with Jupyter Notebook, then what you see here is somewhat familiar. Your code is broken up into different cells that execute independently of each other. Variables that you create are stored in memory and can be accessed in subsequent cells. And this sort of gives you a kind of way to, you know, impose a modular structure on your code so you can test specific areas without having to touch other areas. Has anyone used Mathematica? Oh my God, wait, raise your hand. Okay, all right, cool, yeah. So I was in academia for a long time before not being in academia, and yeah, I lived in Mathematica. doing different things. And you know, the structure of Jupyter Notebooks is basically the same thing, if that helps anybody. So at the very beginning, and I won't belabor the point or anything, there are just some tricky things about Collaboratory. It sets up some kind of virtual machine environment that you live inside of, and then eventually, after enough latency on your end, it wipes out that machine. And any model that you've created, any data that you've downloaded in whatever directory that it was living in is just gone. So that's basically useless. If you want to try to do something like let something train for a couple hours before while you sleep or something, and you come back in the morning, it's gone. As I understand it, that's what I was encountering. There are actually some tricks around this, and that's what the first couple of cells do. It's very uninteresting. It's just stuff you got to do, right? So you got to first mount your Google Drive and get access to that file tree. And then once you've done that, you got to CD into it. And then to run this notebook here, you need to clone our repo that we have over here. And I have that commented out because, well, you obviously only need to do that once. And then that is going to put a copy of our repo into your Drive directory. And then you're free to work with it there and then run the subsequent cells. This cell over here is the last cell that you would kind of need in this special collaboratory environment. Just CDs down into the repo that you will have cloned, and then if you haven't cloned it, you at least need the freshest update of it. So you just sync with the server, pull what's up there right now, and then you're free to go. And if you're familiar with Jupyter Notebooks, then you can think of this cell over here as really the start, where you import all of the packages and libraries that you need to execute the cells down below. And I've tried to make this as easy as possible as easy as possible to just simply play around with. So the variational autoencoder itself, all of the code for that is all wrapped up into this script that's contained in one of the files that's inside of the repo. And you just import it as this object here, and you create different instances of it that'll point to different models. There are some constants and functions that you're going to need in this notebook. I'm not going to go over them right now, so I'm just going to quickly scroll through them and show you just very quickly. I know I need to end right now, but how this thing works. So I've set this thing up to be as flexible as I can right now, so you can basically just specify the shape of the model. So this is a bunch of convolution and deconvolution layers for celebrity stuff, encoder and decoder stuff, and then a lot of other attributes to feed in here. And you can use that to create a model here. So I create an autoencoder model, and I create a variational autoencoder model, and I grab their names. And I use those names as a handle with which to repeatedly call those models in context managers over here like this, and do things like, well, here's one cool thing that you can do. Hopefully all the contents are, yeah, the output is, oh gosh, no. Well, I lost some of the output. Am I even connected right now? Yeah, I am connected. In this white space, you would be seeing an image of the TensorFlow graph visualized in TensorBoard. Oh, there it is. Okay, yeah, yeah. So, you can see this, and you can click within these different things. I don't have time to do that, but you can click within them to look at, the different components that are living inside. So, for example, there's an encoder and decoder, and okay. So there it all is. You can check that out. And subsequent cells, you can train. It takes about 10 minutes to train the autoencoder or the variational autoencoder. Please keep in mind, we're not providing the data for Celeb A. You need to go to the website for that, and then get all of that information, put it in a directory, and then we have some helper functions that can crop out the face images using OpenCV. So you'll need to do all of that first. But provided you do all of that, you can train a model, and you can run these various cells to output the results that you saw in this talk here. And so I welcome you to try it out. Tell me what I've done well, what I've kind of messed up, and what I should think about for a better design, or any bugs that you might see. And I'll take to that and try to make this something cooler. My kind of vision is to make this into a broader project with modular pieces. So one of them is this variational autoencoder. I would like to take a look at GANs next, and I'm really interested in these VGAN combinations. VGAN being kind of a funny acronym that I'm not the first person to make fun of, but I do have this sort of dream where I'm, marrying all these components together and, creating some really cool stuff. So, and hopefully, in the future, I can give a talk to you guys if you're interested about that, and we can see even more. So that's pretty much all I had to say there, and now I'm truly going to close by finding, yes, just the very, oh gosh, now I'm scrolling. Yeah, I just want to mention a little bit about Comp3. So Jason is one of the partners at Comp3, and as he mentioned earlier, I'm a machine learning engineer working there. And I just want to let you guys know about it, that we are an AI and data consulting company. We're local in San Jose. You should check out our website and get some information about us there. And we have resources available, and we work on all kinds of different projects, front and back end ML engineering. And, as you can see from this talk, we also like to, stay fresh on state-of-the-art things and try to pick off little pieces and go into new and exciting areas, such as, in this case, image generation, and expand on that. So reach out to us if you would be interested in anything that we can do for you, and also in possible future extensions on this topic or other topics for this meetup group. And that's all I have to say, so I'll stop there.
Thanks a lot, Stephen.
And of course, any questions that you may have. Yeah.
Wouldn't it be cool if there were more specialized meetups dedicated to mathematical part with all multiple integrals in it, and because currently it is, from my experience, it looks like a rare event. It happens rarely. So it is great that you are willing to make a presentation, but well, it would be good if it would be good to separate meetup, no?
So you're saying expressing interest in maybe having a meetup that would be specific to more diving into maybe a research paper.
Yes.
So something, maybe we get a general show of hands. Previous incarnations of the meetup group, they would pick a paper, and it'd be like usually a smaller group of people, and they would all read the paper and then come and discuss it, maybe in a group of like 7 or so people. Would there be interest in building and having maybe a couple of those types of meetups in the future? Yeah? Okay, cool. So maybe that's something we try, maybe for our next one. We'll pick a paper and just see who's interested. Everyone reads it, comes through and discuss, because then you can really get into the math, you can get into the interesting parts of it. Yeah, that's a good suggestion. Thank you.
Yeah, that sounds like a fun idea.
Cool. Maybe one last question?
I have a question. So this thing about curve,
About what?
about the high dimensional,
Yeah.
anything to do with the curves of dimensionality?
Well, you could think of it as a solution to that. Another very well-known algorithm in data science is PCA, right? So the idea is that your data is living in some high-dimensional vector space, but if you looked at it, it kind of would look like a galaxy, for example, living in a 3-dimensional ambient space, right? So maybe some sort of ellipsoid structure. So it's secretly 2-dimensional somehow. So PCA is sort of a higher dimensional version of addressing that kind of issue. And that's a compression algorithm that is similar to an autoencoder, actually, in the sense that if your autoencoder has only one layer to the encoder and decoder components, then there is a close relationship between the autoencoder algorithm, or at least what it converges to, and PCA. They're not quite exactly the same, but you should be able to transform one to the other. And there's a research paper out there that talks about how to do this, and that paper is actually pretty current, I think within the last 1 or 2 years, which surprises me a little bit, because it seems like such a natural question to ask. So if you're interested in looking for that paper, I think the way I found it was just going to Wikipedia on autoencoders, and then down at the bottom They've got, you know, different links to different papers on the topic. Again, autoencoders have their own zoo of models that are good at specific niche tasks. And you can find it there or just, you know, Google search it and learn more about that.
I was wondering actually follow on to that. So, actually I don't have much background in any of these things, I'm just asking different questions. The KL, is that between the actual latent variables and something, or what's the distance between?
Yeah. So let me just show you the explicit formula. It's actually given right here. So, so it's the second equation over here. So ignore the phi's and the thetas for now. Those are parameters that we don't need to think about. Just pretend that you had two probability distributions Q and P. So then this KL distance metric between them is given by this integral here.
So it's just the relative entropy?
Yes, it is. Yes. Well, I mean, it's a little bit different because I think cross entropy is not going to have this Q up in the numerator over here. And to confess, I have almost zero intuition for why this thing works, other than it, tends to be small when these things are close and tends to be large when they're apart. Mathematically, it's not terribly elegant because it's not a true distance function. It doesn't have the triangle inequality property if you invent a space of probability distributions. But there are ways to patch that up, and mathematicians have worked with those patched up versions as well. But at least for developing ML models and trying to get certain probability distributions to converge to each other, this seems to do a pretty good job, so people use it. And I'm sure that there are plenty of other experts who are gnashing their teeth right now, seeing that I'm missing the fundamental insight that makes this the right thing to work with, but it just seems to be the right thing to work with.
So,
Yeah.
so Z is the output?
Z is the latent variable here.
Okay.
So in this case, these are,
Okay,
yeah,
that
so,
was my question.
yeah, right. So, okay, to make it, let's simplify it even more, right? Because this equation is tailored specifically to this context over here. Just drop the x's and drop the phi's and the thetas. So you just have Q of input, P of input, just two distributions with the same domains.
Actually, you can stick around for a little bit
Yeah,
longer.
yeah.
So I think it's getting late, letting some people go if they want to go, obviously. I want to say thanks again to Dave for letting us use Redis Labs as our space for tonight. Thank you, Stephen, for giving us an awesome talk. And thank you guys for coming. So appreciate it.